algorithm, pseudocode, and complexity. First up, we have the pseudocode. Now, first of all, we have certain number of vertices. We need to add all of them into a set called Q. We initialize all the distances of these vertices to infinite and the previous of these vertices to undefined. And we add all these vertices to the set Q. Okay, now we initialize the distance of source to 0. While Q is not empty, U is the vertex in Q with minimum distance. It is nothing but initially it is nothing but U. Initially is nothing but the source. We remove this U from Q and we find the neighbor of all the neighbors of this particular vertex with the least cost. Once we have found out the neighbors, we'll find out their cost. How? By adding the cost of this node with the least cost plus the distance or the cost between this node and its particular neighbor node. If this new found out cost, which is alt over here, is less than the cost which we already have for this node in Q. Initially, it will be infinite, but there might be cases when we find out the cost of a particular node twice or thrice. So, in those cases, if the newly found cost is less than the existing cost for this particular node, then we update the cost of this node and also update the previous of this node to U. And we return the distance in previous. Again, we go back to Q. We find out the node with the least cost. Then we find out its neighbors. Then we find out the cost of all of its neighbors. If the newly found cost is less than the existing cost, we update it. Else, again, we go back to Q. We find the node with the least cost, find its adjacent nodes, and so on. The process goes on till we find the target node. Once we found the least cost, the target node, our mission or our target is achieved. We have found out the shortest path between the source node and the target node. Next up, we have the time complexity. Now, the time complexity is big of E log V. Why? The reason is that if we have to store V, we have to insert V vertices in the set Q. So it takes big of V time. Next, we have to calculate the shortest distance, which node has the shortest path in Q, which takes log of V time. And since we have to do it for each vertex, we multiply it by V. Next, once we found out the node of the least cost, we have to also find out the cost of its neighbors. More the edges, more the neighbors, because the neighbors are attached to this particular node through edges. To find out the respective cost of vertices, and again to update the cost in Q, it takes log of V time. And since the number of neighbors is equal to number of edges from that particular node, we multiply it by E. So now we have three things: big of V log V, big of E log V, and big of V. And out of these three, big of E log V is biggest. Thus, the time complexity is big of E log V. Next, we have space complexity. We need big of V space for storing the set of V elements and big of V for storing vertices. So space complexity is big of V. Next, I'll talk about A-star algorithm pseudocode and complexity. First of all, the pseudocode. Now, the pseudocode is divided into many steps. First of all, initialize the open list and closed list. Open list is a set of all nodes whose cost has been identified, but we are not yet sure whether it is the shortest path or not to that particular node. And closed list is a set of all nodes whose shortest path is already found out. Okay. Next, while the open list is not empty, while there are some nodes, we'll find out the node with the least F. Pop off this particular node from the open list, and put it into closed list. Why? Because we found out the shortest path to this node. Next, we generate all the skew successors or the neighboring nodes. Now, for each successor, if the successor is the goal, we stop the search. But if it's not, we find out its cost. How? By adding two values, G and H, where H is the heuristic value and G is the value from the source node to the particular node. Once you have added up, now again we check. We check if the node was already present in the open list, and we compare that value to our new value. If our new value is less, then we update the cost of that node in the open list, else we skip this node or the successor. Again, we check in closed list. In closed list, if a new value is less than the existing value in the closed list for that particular node, then we add it to the open list, else we skip the successor. The for loop. When the for loop will end, it means that we have evaluated the shortest path to each of the neighboring nodes. Next, it will push this element q, which has the shortest path, to the closed list, and this will continue until there are nodes present in the set q. So again, we'll go back to q, we'll find the node with the shortest path, we'll find its neighboring nodes, we'll find the cost of the neighboring nodes, we'll compare it in the open list, in the closed list, and thus after that we'll add the node q to the closed list. Why? Because all its neighboring nodes paths has been evaluated, the shortest path has been evaluated, so we can add the node q to the closed list, and this will end the while loop. Now the while loop will continue until q is empty, or if we have reached the target node. Once we have reached the target node, which means we have found out the shortest distance to it, and thus we have achieved our target. Next, moving towards the time complexity. The time complexity of A star depends upon the branching factor. We can visualize A star algorithm as a tree. If there are more branches, then naturally the time taken to reach the target will be more. Also, it depends on the depth of the target node. If the target node has a good depth, then naturally more time will be taken to reach the node. Thus, the time complexity is big of p raised to d. Next, we'll talk about space complexity. Now, the space required is to store the closed list, open list, and the nodes. Thus, the space complexity is big of V, where V is the number of vertices.